Hello, this is Dr. Kraus with video 1 for EGR 345. What is a transfer function? Transfer functions are foundational to dynamic systems and feedback control courses, especially on the dynamic systems side. I would say that's the main topic. And so we're going to, over the course of the semester, dig pretty deep on this, but I want to start with an introduction today. A transfer function is an input-output model of a dynamic system. Dynamic system, input-output. So that ought to immediately raise in my mind at least two follow-up questions. First of all, what is a dynamic system? And then what did I mean by putting these parentheses in S after the input and output? What is up with S? So a dynamic system, first of all, let's define the term system. I think that sometimes gets thrown around in engineering without a clear definition. And so by system, I simply mean a collection of components that makes up a whole. So a bicycle is a system made up of different components. A refrigerator is a system made up of different components. A biomedical device is a system made up of different components. And so they all work together to accomplish some end. An electrical circuit has different components that make up an electrical system, so on and so forth. And when we say dynamic system, what we mean, dynamic here is the opposite of static, and what we mean by that is a system whose input-output relationship involves a differential equation. So if f of t, f is a function of t and it's my input, and x of t, x is a function of t and it's my output, but the equation also involves the first and second derivatives, so dx dt and d squared x dt squared, x dot and x double dot. So I've got a differential equation between the input and output of my system. That makes it a dynamic system. Another question that we will probably come at 3 or 4 different ways and different times because this causes a lot of confusion. Some students really kind of fixate on what is S, and they kind of get concerned about that. Like if I said that y of t was equal to the cosine of 2 pi t, you would never ask me the question, what is t? We all know that t is just a variable. It's an independent variable. It represents time, and it can be anything from 0 to infinity. So S is the Laplace variable. I get that it's new or different and maybe a little confusing. It also can take on complex values, and so that can be a little weird. But it's just a letter. Mostly for our purposes, I wanted you to think of S in terms of a differential operator. It represents differentiation with respect to time. So what I mean by that is if we can assume 0 initial conditions, and we'll talk later about what to do when that's not the case. But if for now we can assume 0 initial conditions, then when I take the Laplace of df dt, or df dt is the same as f dot. So when I take the Laplace of f dot, I just get S times whatever the Laplace transform of f is. So we take f of t, we Laplace transform it, we write it as capital F of S. So differentiation with respect to time gets converted to simply multiplying by S. And similarly, integration with respect to time gets converted to division by S. So what that ultimately ends up being or meaning is that differential equations can get replaced by algebraic equations. Instead of all these dots and double dots, I just multiply by S. And algebraic equations are much, much easier to solve. So, coming at this in a slightly more careful way, a transfer function is an input-output model of a dynamic system in the Laplace domain or in the S domain. So g of S is a transfer function of our system. U of S is the Laplace transformed representation of the input, and y of S is the output. I can find U of S by looking up U of t in a table, and then when I'm ready to find y of t, I break up U of S and look those components up in a table, and the table helps me move back and forth between the time domain and the S or Laplace domain. So the big idea is if I know the transfer function of my system, I can find the Laplace transform of my input, and when I multiply those together, I find my output in the Laplace domain. So y of S is just g of S times u of S, but this is ultimately the solution of a differential equation, essentially. And then, if I need to get back to y of t, I need to take y of s, and we'll have a special approach called partial fraction expansion that helps us break y of s into smaller components that happen to be in our table, so we can look up those components and then add them together and find y of t. So, why do I say that transfer functions are the foundation of dynamic systems? Why are they so powerful? What can they do for us? One, if I have the transfer function of a system, I can find the response of that system to any input. Any. We'll have certain ones that we kind of use as our main kind of test inputs, but ultimately I can find the response to any input. Now, if I was a mathematician, there's a couple of caveats there, but they're pretty silly, so we won't talk about that for now. And I can do that either symbolically, we'll learn how to do partial fraction expansion and Laplace transform analysis by hand, but also through numeric simulations, and we'll learn how to take transfer functions and create them in Python and then pass inputs to them and get outputs out of them and plot those outputs and see what happens. But if there's something I don't like about the dynamic response of my system, maybe it's too slow, maybe it's not accurate, maybe it's easily blown off course, we would call that a disturbance input or an unwanted input, then I can measure the output of my system and use that to determine the future inputs to the system, and that's called feedback control. Well, if I want a feedback control, I'm really best off if I can design that. And so if I want to design a feedback control system, then a transfer function helps me do that. And there's many tools, such as the root locus or Bode compensator design or whatever, as well as tools to simulate the closed loop response. So having a transfer function allows me to design a feedback control system that can help my system respond faster or reject unwanted inputs or reduce vibrations or otherwise eliminate unwanted dynamics. So it can do a lot of really powerful things for us. So, if transfer functions are so powerful, and they are, and we're going to use them throughout the course, and they're going to do lots and lots of great stuff for us, how do we find them? And so we're going to talk about this two main ways in this course that we're going to find our transfer functions. One is coming up with a differential equation model. That's going to use things like what engineering professors like to call first principles, either Newton's laws or Kirchhoff's laws or whatever, to come up with a differential equation model for whatever system we're talking about. But sometimes it's just not obvious exactly what laws apply to a system, and or real-world components sometimes don't easily lend themselves to super simple analysis. And so sometimes we just need to find a transfer function based on experimental data. And we're going to learn how to do that both in the time domain, where I just measure a voltage with respect to time, and I look at the input-output relationship, and I find a way to kind of curve fit a model to them. But some of our data, we're also going to use the fast Fourier transform, or FFT, to convert it into the frequency domain, and we're going to generate a really powerful graph called a Bode plot that's going to help us determine the transfer function for various experimental systems. So the core idea, and we'll go in coming lectures into a decent amount of detail on proving why Laplace works and how Laplace works, and everybody loves a good engineering derivation, so I can prove to you that I know what I'm talking about. Good times for everybody. But for now, the main thing I need you to know is, again, assuming zero initial conditions, we'll talk about that particular detail later as well. But if I take the Laplace transform of a derivative with respect to time, or a single dot, I multiply by s. When I take the Laplace transform of a double dot, because in mechanical systems, a lot of times we're dealing with accelerations, and so we have x double dots coming out of Newton's laws, then I get an s squared times my f of s. So for example, if I started with this differential equation model, which we talked about a couple slides back, when I Laplace transform it, x double dot becomes s squared times x of s. X dot becomes s times x of s, and then x will just become capital X of s, and little f of t will simply become capital F of s. So now I can do some algebra on this, I can pull an x of s out of everything on the left-hand side, and then I could take this and divide it across, and ultimately I go from here to this is the transfer function of this system. G of s, which is G is a count. I don't know why certain letters just get locked into certain things, but G of s is a plant transfer function. Plant is another controls term we'll talk about later. Generally, it just means the thing that you're trying to analyze or control, your dynamic system, whatever your open loop system is. Once I have G of s, I can find x of t for any f of t. And so this is my transfer function. So not only is this an input-output model of my dynamic system in the Laplace domain, but they also generally work out to be fractions involving polynomials in S. So I'll have some numerator polynomial, in this case just 1, and then I'll have some denominator polynomial in S, and so that is another hallmark of a transfer function. And so what we're going to work on next and talk about in class is, first of all, how do I find this for some different simple systems? And then once I have that transfer function, how does this process work as far as given an f of t, how do I find the corresponding x of t?